Well, welcome back to our course on system engineering. We're going to be talking about engineering design. And just to give context here for where we are in our overall class. And so we talked about the foundations, then we have the three major parts in the life cycle process. The first being the concept development, the second being the engineering development, and the third be the post-development stage. And so now we're right in the middle of the engineering development for just to give some context to where we're at. So let's go ahead and give into some of the information that's related to this. And first of all, we'll start out with implementing the system building blocks. The engineering design phase is that part of a development of a new system, which is concerned with designing of all the component parts of the system so that they will fit together as an operating whole that meets the system operational requirements, and is an intensive and highly organized effort focused on designing components that are reliable, maintainable, and safe under all conditions to which the system is likely to be subjected, and are producible within established costs and schedule goals. With the general design approach required to meet the above objectives, presumably has been established in previous phases, the engineering design phase is where detailed internal and external interfaces are established and the design is first fully implemented in hardware and software. The advanced development phase for any previously unproven components should be further developed to the point where all the significant issues regarding their functional and physical performance have been resolved. However, experience in developing complex new systems has shown that some unknown unknowns almost always escape detection until later, revealing themselves during component design and integration. Such eventualities should therefore be anticipated in contingency planning from the engineering design phase. Well, let's consider the place of the engineering design phase in the system life cycle. And so we're coming back to this familiar figure. And so we're detailing here the engineering design part of that. So the figure shows the place of the system of the engineering design phase, and the system engineering life cycle follows the advanced development phase and precedes the integration and evaluation phases. Its inputs from the advanced development phase are seen to be system design specifications and a validated development model of the system. Other inputs, which are not shown, include applicable commercial components and parts, and the design tools and test facilities that will be employed during this phase. Its outputs to the integration and evaluation phase are detailed test and evaluation plans and a complete set of fully engineered testing component. Program management planning documents such as the work breakdown structure and the system engineering master plan, as well as the test and evaluation master plan or their equivalents, are utilized and updated in this process. So the figure shows the integration and evaluation phase usually begins well before the end of the engineering design to accommodate test planning, test equipment design, and related activities. Okay, well, I was talking to the previous figure here, which shows you the phases. And here in this document, it shows the engineering design phases and relationships to the integration and evaluation. So you can just pause the video and look over this if you'd like to spend more time on that. Next, let's think about the design materialization status. The change in system materialization status during the engineering design phase is schematically shown here in the table. It is seen that the actions visualized, defined, and validated in previous phases are replaced by more decisive terms, design, make, and test, representing implementation decisions rather than tentative proposals. This is characteristic of the fact that in this phase, the conceptual and development results of the previous phases finally come together in a unified and detailed system design. At the beginning of the engineering design phase, the design maturity of different components is likely to vary significantly. and these variations will be reflected in differences in component materialization status. For example, some components that were derived from a predecessor system may have been fully engineered and tested in substantially the same configuration as the selected as that selected for the new system, while others that utilize new technology or innovative functionality may have been brought only to the stage of experimental prototypes. However, by the end of the engineering design phase, such initial variation in component engineering status must be eliminated and all components fully materialized in terms of detailed hardware and software design and construction. A primary effort in this phase is the definition of the interfaces and interactions among internal components and with external entities. Experience has shown that aggressive technical leadership by system engineering is essential for the expeditious resolution of any interface incompatibilities which are brought to light during engineering design. So thus we see we're in the engineering development. In the last lecture, we talked about advanced development. So here we are in the engineering design portion of this. Plus, we want to be thinking about this system engineering method in the engineering design. And so we have this flow diagram that we've shown before, but now we'll be thinking about it in terms of the engineering design part. So the principal activities in each of the 4 steps in the systems engineering method during the engineering design are briefly stated in the textbook, and I'll just go over them now, and we're showing them in the figure. So steps 3 and 4 will constitute the bulk of the effort in this phase. So typical activities include the requirements analysis, analyzing system design requirements for consistency and completeness, 2, identifying requirements for all external and internal interactions and interfaces, 2, functional analysis and design. And this gets into 3 things: analyzing component interactions and interfaces and identifying design, integration, and test issues, 2, analyzing detailed user interaction models, and 3, designing and prototyping user interactions. 3, concerning the conceptual component design, there's 3 things that are done here: laying out preliminary design of all hardware and software components and interfaces. 2, after review, implementing detailed hardware design and software code. And 3, building prototype versions of engineered components. For design validation, there's 3 things that are conducted. First, conducting test and evaluation of engineered components with respect to function, interfaces, reliability, and producibility. 2, correcting deficiencies. And 3, documenting product design. Okay, well, the bulk of what we'll be talking about in this lecture will be highlighted in 4 slides, and we'll be spending a fair amount of time on each one. And so those 4 things are requirements analysis, number 1. Number 2, functional analysis and design. Number 3, component design. And number 4 is design validation. And so we'll take them one at a time. And for component design, we'll have a couple slides that we'll break up into more detail. So first of all, for requirements analysis, and so in the advanced development phase, the system functional specifications were translated into a set of system design specifications that define the design approach, selected and validated as fully addressing the system operational objectives. As in the previous phases of the development process, these specifications must now be analyzed again for relevance, completeness, and consistency to constitute a sound basis for full-scale engineering. In particular, the analysis must consider any changes occurring due to the passage of time or external events. So in terms of system design requirements, it will be recalled that the focus of the advanced development phase was on those system components that require further maturation in terms of analysis, design development, and or testing to demonstrate their full validity. These are the components that represent the greatest development risk, and hence their design approach must be carefully analyzed to ensure that the residual risk have been reduced to manageable levels. For example, components with initially ill-defined external interface descriptions must be re-examined to resolve any remaining uncertainties. Components that were identified as involving some risk, but not to the extent of requiring special development effort, and previously proven components that will be required to perform at higher levels or in a more stressful environment must be particularly scrutinized at this stage. The results of these analyses should be inputs to the planning of risk management during the engineering design. We have engineering system interface requirements and a couple of things related to that, which we'll get into. So first of all, since the whole system has not been physically assembled in previous phases, it is likely that the design of the interfaces with the environment has been considered less than rigorous. Hence, a comprehensive analysis of system-level environmental interfaces must be carried out prior to the initiation of engineering design. Let's next get a little bit more detailed and think about user interfaces. So as noted previously, the functional interactions and physical interfaces of the system with the users are not only often critical, but also difficult to define adequately. This situation is abrogated by the fact that potential users of the new system do not really know how they can best operate it before the first physically interact with it. Thus, except for very simple human-machine interfaces, a prototype model of the user consoles, displays, and controls should be constructed at the earliest practical time to enable the users to examine various responses to system inputs and experiment with alternative interface designs. If this has not been done adequately in the advanced development phase, it must be done early in engineering design. The user interfaces relate to system maintenance, involve fault isolation, component replacement, logistics, and a host of related issues. Interface design is often given only cursory attention prior to the engineering design phase, an omission that is likely to lead to the need for significant redesign of previously defined component interfaces. Then we also have environmental interfaces. In defining external interfaces subject to shock, vibration, extreme temperatures, and other potentially damaging environments, it is essential to again consider all stages of the system's life, including production, shipment, storage, installation, operation, and maintenance, and to anticipate all of the interactions with the environment during each step. Interface elements such as seals, joints, radiation shields, insulators, shock mounts, and so on should be reviewed and redefined if necessary to ensure their adequacy in the final design. Some of the above subjects are treated more fully in a later topic that we'll get into, user interface designs. We also have assembly and installation requirements. In addition to the usual design requirements, the system design must also take into consideration all special requirements for system assembly and installation at the operational site. This is especially important for a large system that must be shipped in sections. An example is a shipboard system, subsystems of which have to be installed below decks in an existing ship. In this case, the size of the hatches and passageways will dictate the largest object that can be passed through. System installation above aboard aircraft is another example. Each building have load and size limits on freight elevators. In any case, when on-site assembly is required, the system design must consider where the system will be cut and how it will be reassembled. If physical mating is implemented by bolts, for example, then the location and size of these fasteners must be taken into account in the size and position of the wrenches needed for assembly. Many developers may have been embarrassed when they realized that there was not enough elbow room to perform a prescribed assembly procedure. Another on-site problem can occur when the assembly process is found to be difficult and slow to perform. A classic example concerns a suspended walkway that was installed in a large Midwestern hotel lobby. During a large evening dance party, a number of people were dancing on the elevated walkway, causing it to collapse with attendants' loss of life. The investigation of the accident revealed that a design change had been made at the assembly site because of the originally specified long threaded supporting rods were difficult to install. So-called quote trivial design change was made to permit easier assembly, but it increased the load on the rod structure by a factor of 2. The fault was attributed to those involved in the design change. However, it can be argued that if the original designers had given more attention to the difficulty of assembly process, the problem and the resulting accident might not have occurred. We also have risk mitigation. And so this is covered in another lecture, another chapter. A necessary step is the planning of the development and engineering process is the consideration of program risk. In the advanced development phase, risk assessment was used to refer to the process of identifying components that required further maturation to eliminate or greatly reduce the potential engineering problems inherent to the application of new technology or component functionality. By the beginning of the engineering design phase, those risks should have been resolved through further development. This in turn should have reduced the remaining program risk to a level that could be tolerated through the application of risk management, a process that identifies and seeks to mitigate the likelihood and impact of residual risk. Methods for mitigating risk are discussed briefly in a later section, and we'll get to that shortly. Finally, in terms of critical design requirements, to the extent that previous analysis has shown that a particular requirement places undue stress on the engineering design, this is the last opportunity seriously to explore the possibility of its relaxation and thus reduce the risk of unsuccessful design. Next, we'll get into functional analysis and design, and the things that we're going to consider are modular configuration, software design, and user interfaces. And since I'm going to go into a little bit more details, I expanded them towards the bottom of the slide, and you can be following what we'll cover here. So the principal focus of the engineering design phase is on the design of the system components, insofar as the functional definition of the components is concerned. It may be assumed that the primary allocation of functions has been accomplished in previous phases, but that the definition of their mutual interactions has not been finalized. Primary objective of the functional analysis and design step is to define the interactions of components with one another and with the system environment in such a way as to maximize their mutual interdependence. Mutual independence, and thus facilitate their acquisition, integration, and maintenance and the ease of future system upgrading. So what we're talking about in this part of this chapter is looking at the stresses. This area stresses 3 important areas of functional analysis and design. I've already mentioned them. I have it listed. The modular configuration, simplifying interactions among system components and the environment. 2, software design, defining a modular software architecture. And 3, user interfaces, defining and demonstrating effective human-machine interactions. Well, let's talk about these in more detail one at a time. So for modular configuration, the single most important objective of the functional analysis and design step in the engineering design phase is to find the boundaries between the components and subsystems so as to minimize their interactions. This is essential to ensure that, and we have 4 things we want to ensure. 1, each component can be specified, developed, designed, manufactured and tested as a self-contained unit. 2, when assembled with the other components, a component will perform its function properly and without further adjustments. 3, a faulty component can be replaced directly by an equivalent interchange component. 4, a component can be upgraded internally without affecting the design of other components. A system designed with the above characteristics is referred to a modular or sectionalized. These characteristics apply to both hardware and software components. They depend on physical as well as functional interactions, but the latter are fundamental and must be defined before the physical interactions can be established. Then in terms of functional elements, the system functional elements are examples of highly modular system building blocks. These building blocks were selected using 3 criteria. So significance, each functional element performs a distinct and significant function, typically involving several elementary functions. Singularity, each functional element falls largely within the technical scope of a single engineering discipline. Commonality, the function performed by each element is found in a wide variety of system types. So each of the functional elements is the functional embodiment of the type of component element, which is a commonly occurring building block of modern systems. Their characteristic of commonality results from the fact that each is highly modular in function and construction. It follows that the functional elements of a new system should use standard building blocks whenever practical. Let's think about an example. For a modular design, we'll consider a Navy guided missile. So in the early 1950s, the Navy undertook to expedite the transition of its first surface-to-air guided missile from development to large-scale production. Guided missile technology was still in its early stage, making this a very ambitious undertaking. However, engineering proceeded relatively successfully until missile components built in the factory began to be assembled and tested. Here, the process came to a halt because the individual components were neither sufficiently stable nor independent enough to be assembled without subsequent readjustment. Even worse, adjusting one also affected the performance of other interacting components, and as a consequence, the missiles regularly failed to pass their final acceptance tests. This problem effectively stopped production until extensive redesign was accomplished to increase component tolerance, eliminate most of the adjustments, and make individual components much more independent. Ultimately, it required complete reconfiguration of the components some years later to a highly modular form to make the production process relatively effective and efficient. Next, we can be thinking about software design. So, as noted previously, the development and engineering of software components are different from that of hardware components. And we'll discuss a few selected subjects related to the engineering design. First, let's refer to prototype software. So another lecture and chapter noted that extensive use of software throughout most of modern complex systems usually makes it necessary to design and test many software components in prototype form during the advanced development phase. Common instances of this are found in embedded real-time programs and user interfaces. The existence of such prototype software at the beginning of the engineering design phase presents a problem of whether or not to use it in the engineered system, and if so, just how it should be adapted for this purpose. Redoing the prototype software from scratch can be extremely costly. However, its reuse requires careful assessment and revision where necessary. So the following conditions are necessary for the successful reuse. So we have 3. First, the prototype software must be of high quality, that is, designed and built to the same standards that are established for the engineering version. 2, changes in requirements must be limited. 3, the software should be either functionally complete or compatible with directly related software. Given the above conditions, modern computer-aided software design tools are available to facilitate the necessary analysis, modification, and documentation to integrate the prototype software into the engineered systems. We also have software methodologies. 2 principal methodologies are used in software analysis and design: structured analysis and design, and object-oriented analysis and design. The former and in more mature methodology is organized around the functional units, generally called procedures or functions, and assembled in modules or packages. In good structured design, data values are passed between procedures by means of calling parameters with a minimum of external addressed data. On the other hand, object-oriented analysis and object-oriented design are more recent methods of software systems development and are widely believed to be inherently superior in managing complexity, which is a critical problem in large information-rich systems. Using object-oriented methods in developing hardware and combined hardware and software systems has become more commonplace and usually referred to object-oriented system engineering, OOSE. The particulars of this method will be discussed later. Accordingly, today's systems engineers need to know the basic elements and capabilities of these methodologies in order to evaluate their appropriate place in system development. Finally, we will talk more in detail about user interface design. Among the most critical elements in complex systems are those concerns with the control of the system by the user, analogous to the steering wheel, accelerator, shift lever, and brakes in the automobile. System terminology, those elements are collectively referred to as the user interface. Their criticality is due to the essential role they play in the effective operation of most systems and to the inherent problem of matching a specific system design to the widely variable characteristics of the many different human operators who will use the system during its lifetime. If several individuals operate different parts of the system simultaneously, their mutual interactions present additional design issues. The principal elements involved in user control include displays. Presentations provide to the user containing information on system status to indicate need for possible user action. They may be dials, words, numbers, or graphics appearing on a display screen or a printout, sound, or other signals. There's user reaction, user interpretation of the display based on knowledge about system operation and control, and consequent decisions on actions to be taken. User commands, user actions to cause a system to change its state or behavior to that desired. It may be movement of a control lever, selection of an item from a display menu, a type command, or another form of signal to which the system is designed to respond. There's also a command actuator device designed to translate the user's action into a system response. This may be a direct mechanism or electrical link or automated system, a computer that interprets the user command and activates the appropriate response devices. The design of a user system interface is truly a multidisciplinary problem, as the above list implies, and hence the domain of system engineering. Every human, even human factors engineering, considered to be a discipline itself, is actually fragmented into specialties in terms of the sensory and cognitive aspects. While much research has been carried out, quantitative data on which to base engineering design is sparse. Thus, each new system presents problems peculiar to itself and often requires experimentation to define its interface requirements. The increasing use of computer automation in modern systems has brought with it the computer-driven display and controls as a preferred user interface medium. A computer interface has the facility to display information in a form process to give the user a clearer and better organized picture of the system status, simplify the decision process, and offer simpler and easier modes of control. Finally, related to that, we have functional system design diagrams. As a component of a complex systems are integrated, it becomes increasingly important to establish system-wide representations of the functional system architecture to ensure its understanding by all those concerned with designing the interacting system elements. Next, we'll talk about component designs, and I'll have 2 slides that cover this, and there is a lot of details here. There are some detailed mathematical development on the next slide that I'm going to skip, and you can refer to the textbook to get some more of those details. So in terms of component design, the object of the component design step of the engineering design phase is to implement the functional designs of system elements as engineered hardware and software components with compatible and testable interfaces. During this phase, the system components that do not already exist as engineered items are designed, built, and tested as units to be integrated into subsystems and then assembled into an engineering prototype in the integration and evaluation phase. The associated engineering effort during this phase is more intense than any other time during the system lifecycle. During the design of any component new system, unexpected problems inevitably occur. Their timely resolution depends on quick and decisive action. This high level of activity and the potential impact of an unforeseen problem on the successful conduct of the program tend to place a severe stress on the system engineering during this period. In the development of major defense and space systems, the engineering design effort is performed in 2 steps, designated preliminary design and detailed design. So we're seeing the PDR and CDR here in this chart in red. That's what we're referring to. Although preliminary design is typically started under systems architecting, many official programs continue to establish a subphase where the initial architecture is translated into a preliminary design. Each step is followed by a formal design review by a customer before the succeeding step is authorized. The purpose of this highly controlled process is to ensure very thorough preparation prior to commitment to costly full-scale implementation of the design into hardware and software. This general methodology, without some of its formality, may be applied to the system development. The level of system subdivision on which the above design process is focused is called a configuration item. The level responds most closely to referred to as a component. Should be noted that in common engineering parlance, the term component is used much more loosely than in what we're doing in this book and in this lecture, and sometimes is applied to lower level system elements, which are identified here as subcomponents. So configuration items and configuration baselines will be discussed later in a future chapter. So that's going to be, and just double check that. Yeah, no, I'm sorry, it will be later in this lecture. Well, let's focus in more details. Let's first talk about preliminary design. The object of preliminary design is to demonstrate that the chosen system design conforms to system performance and design specifications and can be produced by existing methods within established constraints of cost and schedule. It is thereafter provides a framework for the next step, detailed design. The bulk of the functional design effort is properly part of the preliminary design. Typical products of preliminary design include design and interface specifications, supporting design and effectiveness trade studies, mockups, models, and breadboards, interface designs, software top-level design, development, integration, and verification test plans, engineering specialty studies. So major system engineering inputs and review are essential for all of the above items. Of particular importance is the manner in which the functional models defined in the functional design process are implemented in hardware and software. Often this requires detailed adjustments in the boundaries between components to ensure that physical interfaces as well as functional interfaces are simple as practicable. To the extent that the advanced development phase has not resolved all significant risks, further analysis, simulation, and experiments may have to be conducted to support the preliminary design process. Well, let's now think more formally with the preliminary design review. In government programs, the preliminary design review, PDR, is normally conducted by the acquisition agency to certify completion of preliminary design. For major commercial programs, company management acts as the role of the customer. The process is frequently led or supported by a commercial or nonprofit systems engineering organization. The review may last for a few or many days and may require several follow-on sessions if additional engineering is found to be required. The issues on which PDR is usually centered include major interfaces, risk areas, long lead items, and system-level trade-off studies. Design requirements and specifications, test plans, and logistics support plans are reviewed. System engineering is central to the PDR process and must be prepared to deal with any questions that may arise in the above areas. Prior to the formal PDR, the development team should arrange for an internal review to ensure that the material to be presented is suitable and adequate. The preparation, organization, and qualification of the review process are critical. This is no less important for commercial systems, even though the review process may be less formal, because success of the development is critically dependent on the quality of design of this at this stage. The completion of preliminary design corresponds to the establishment of the allocated baseline system configuration. Then we get into detailed design. The objective of detailed design is to produce a complete description of the end items constituting the total system. For large systems, a massive engineering effort is required to produce all of the necessary plans, specifications, drawings, and other documentation necessary to justify the decision to begin fabrication. The amount of effort to produce a detailed design of a particular component depends on its maturity, that is, its degree of previously proven design. For newly developed components, it is usually necessary to build prototypes and test them until simulated operating conditions to demonstrate that their engineering design is valid. These products of detailed design include draft production specification. So sometimes there's letters associated with this one, so it would be C, D, and E specs. Subsystem detailed engineering drawings, prototype hardware, interface control drawings, configuration control plan, detailed test plan and procedures, quality assurance plan, and detailed integrated logistic support plans. System engineering inputs are especially important to the interface design and test plans where necessary. Detailed analysis, simulation, component test, and prototyping must be performed to resolve risk areas. Now let's talk about the critical design review. General procedures for the critical design review of the products of detailed design are similar to those for the PDR. The CDR is usually more extensive and may be conducted separately for hardware and software configuration items. The CDR examines drawings, schematics, data flow diagrams, test and logistics supply plans, and so on, to ensure their soundness and adequacy. The issues addressed in the CDR are partly predicted on those identified as critical in the PDR and therefore are scheduled for further review in light of the additional analysis, simulations, breadboard or brass board, or prototype tests conducted after the PDR. As in the case of PDR, system engineering plays a critical role in this process, especially in the review of interfaces and plans for integration and testing. Similarly, internal reviews are necessary prior to the official CDR to ensure that unresolved issues do not arise in the formal sessions. But if they do, system engineering is usually assigned the responsibility of resolving the issues as quick as possible. The completion of detailed design results in the product baseline. Well, we also want to talk about a few other things here that are included in the textbook. And so first of all, computer-aided design. The microelectronic revolution has profoundly changed the process of hardware components design and fabrication. It has enabled the development and production of increasingly complex systems without corresponding increases in cost and degradations in reliability. The introduction of computer-aided design, or CAD, of mechanical components has completely changed how such components are designed and built. Even more dramatic has been the explosive development of electronics in the form of microelectronic chips of enormous capability and power, and their principal product, digital computing. We also have mechanical components. CAD permits the detailed design of complex mechanical shapes to be performed by an engineer at a computer workstation without making conventional drawings or models. The design takes form in the computer database and can be examined in any position, at any scale of magnification, and any cross-section. This is especially true in 3D design and fabrication. The same database can be used for calculating stresses, weight positions relative to other components, and other relevant information. When the design is completed, the data can be transformed into fabrication instructions and transferred to digitally driven machines for computer-aided manufacturing, CAM, of exact replicas of the design. Can also generate production documentation in whatever form may be required. One of the dramatic impacts this technology has on the design and manufacturing process is that once a part has been correctly designed and built, all subsequent copies will also be correct within the tolerances of the production machines. An equally major impact is on the ease of integrating mechanical components with one another. Since the physical interfaces of components can be specified precisely in 3 dimensions, 2 adjacent components made to a common interface specification will match exactly when brought together. Today, a complex microwave antenna can be designed, fabricated, and assembled into a finely tuned device without the months of cut and try testing that used to be characterized antenna design. The technique has also largely eliminated the need for elaborate jigs and fixtures previously used to make parts fit a given pattern, or specially built gauges or other inspection devices to check whether or not parts conform to established tolerances. Plus, we have electronic components. The design of most electronic components has been revolutionized by modern technology, even more than that of mechanical components. Processing is almost entirely digital, using standard memory chips and processors. All parts such as circuit cards, card cages, connectors, and equipment racks, and so on, are purchased to strict standards. All physical interfaces fit because they are made to standards. Further, in digital circuits, voltage are low, there is little heat generation, and electrical interfaces are digital streams. Input and outputs can be generated and analyzed using computer-based test equipment. Most circuits are assembled on standard circuit cards and interconnects by program machines. Instead of being composed of individual resistors, capacitors, transistors, and so on, most circuit functions are frequently incorporated into circuit chips. This design and fabrication of chip represents a still higher level of automation than that of circuit boards. The progressive miniaturization of base components and of their interconnections has resulted in the doubling of component density and operating speeds every 18 months. And so this is something that's been called Moore's Law, which recently has reached its end. It's not really following along in that predictable trend. But that was true since the early 1980s. However, the cost of creating an assembly line for a complex new chip has progressively mounted into hundreds of millions of dollars, restricting the number of companies capable of competing at the production of large memory and processing chips. On the other hand, making smaller customized chips is not prohibitive in cost and offers the advantage of high reliability at affordable prices. Companies that handle high power and high voltage, such as transmitters and power supplies, generally do not lend themselves to the above technology, and for the most part must still be custom built and designed with great care to avoid reliability problems. In terms of system engineering considerations, to the system engineer, these developments are vital because of their critical impact on component cost, reliability, and often design feasibility. Thus, system engineers need to have firsthand knowledge of the available automated tools, their capability and limitations, and their effect on component performance, quality, and cost. This knowledge is essential in judging whether or not the estimated performance and cost of proposed components are realistic and what their design takes adequate advantage of such tools. It is also important that system engineers be aware of the rate of the improvement of automated tools for design and manufacture to better estimate the capabilities at the time they will be needed later in the system development cycle. This is also important in anticipating competitive developments and hence the likely effective life of the system prior to the onset of obsolescence. So the textbook talks about a couple examples. We'll just quickly go through this. The International Space Station, something called NextGen, and then Ford Motor Company. The International Space Station, ISS, has 15 countries participate in the development of the station. Integration was a challenge due to the differing levels of information on the modules and the varying technical practices. Each partner had to manage their own technical development as well as schedule and budget, as well as integrate the other partners' products. The F-35 Joint Strike Fighter program had a multi-country participation with up to 600 suppliers in 30 countries. The Next Gen Air Transportation System, or NextGen, project faced development on a much larger scale in order to modernize air transportation throughout the entire country, relying on global positioning system and inertial navigation systems capabilities to safely route the increasing number of aircraft throughout the country. Using this precise navigation, the aircraft are now able to fly in parts of the country without ground controlled direction, which can improve fuel efficiency by taking a more direct path rather than operate in tightly defined air corridors. There are many stakeholders to include governance, the United States Transportation Network, and external factors are out there. The Ford Motor Company matured its design process, notably with the Ford production system, where changes in production development occurred in the mid-2000s. Ford started with its original decentralized product development process that had differences from their manufacturing plants and changed to an approach to manufacture and use a series of common parts in their automobiles. This led to development of car architectures to plan how these parts fit together in various models. Communications across functional teams were emphasized, as well as focusing on customer desired value in order to produce cars that the public wanted to purchase. Digital tools were developed to make the design a more repeatable process, as well as capture the corporate knowledge in the design. Continuing on with the second half of component design, we'll talk about reliability, maintainability, availability, and producibility. And there are some large sections that give some mathematical development that I'm going to skip. So I would refer you to the textbook to read over that. So first, in terms of reliability, the reliability of a system is the probability that a system will perform its function correctly for a specific period of time under specific conditions. Thus, the total reliability of a system is a probability that every component on which it functions depends correctly. Then there's an extensive section on the equation, mathematical development, and some rough proofs. I'm going to skip that. Moving on, a number of specific reliability issues must be left entirely to the discretion of the component designers. These issues should not only be examined at formal reviews, but also be subject to oversight throughout the design process. Such issues include external interfaces. Surfaces exposed to the environment must be protected from corrosion, leakage, radiation, structural damage, thermal stress, and other potential hazard. Component mounting. Systems subject to shock or vibration during operation or transport must have suitable shock mountings for fragile components. Temperature and pressure. Systems subject to extremes of temperature and pressure must provide protective controls at either the system or component level. Contamination. Components susceptible to dust and other contaminants must be assembled under clean room conditions and sealed if necessary. High voltage components. Components using high voltage, such as power supplies, require special provision to avoid short circuits or arcing. Workmanship. Parts requiring precise workmanship should be designed for easy inspection to detect defects that could lead to failures in operation. And finally, potential hazard. Components that may present operational hazards if not properly made or used should be designed to have large reliability margins. These include rocket components, pyrotechnics, hazardous chemicals, high pressure containers, and so on. Well, related to reliability, we want to be thinking about software reliability. Software does not break, short circuit, wear out, or otherwise fail from causes similar to those that lead to most hardware failures. Nevertheless, complex systems do fail due to malfunctioning software as often and sometimes even more often from hardware failures. Anyone whose computer keys has locked up or has tried to buy an airline ticket when the computer is down has experienced this phenomenon. With systems increasingly dependent on complex software, its reliability is becoming even more critical. Software operating failures occur due to imperfect code, that is, computer program deficiencies that allow the occurrence of unintended conditions, causing the system to produce erroneous output, or extreme cases to abort or crash. Examples of conditions that cause such events are infinite loops, overflows of memory space allocated to data arrays, and mishandling of external interrupts. There is no possibility of finding all the deficiencies in complex code by inspection, nor is it practical to devise sufficiently exacting tests to discover all possible faults. The most effective means of producing reliable software is to employ experienced software designers and testers in combination with disciplined software design procedures as high modular program architecture, disciplined programming language with controlled data manipulation, disciplined coding conventions requiring extensive comments, design review and code walkthroughs, prototyping of critical interfaces, formal configuration management, independent verification and validation, and finally, endurance testing to eliminate infant mortality. We also have redundancy that's part of this. So complex systems that must operate extremely reliable, such as air traffic control systems, telephone networks, power grids, and passenger aircraft, require the use of redundant or backup systems or components to achieve the required level of uninterrupted operation. If a power grid line is struck by lightning, its load is switched to other lines with a minimum disruption of service. If an aircraft landing gear motion fail, it can be cranked down manually. Air traffic control has several levels of backups to maintain safety operation in case of failure of the primary system. The textbook walks through some equations and some derivations. I'm going to skip over that as well, and you can feel free to look over that in detail in the textbook. So what are some techniques to increase reliability? Several techniques exist to increase or even maximize reliability within a system design. Several have been discussed already. System modularity, which increases by increasing the modularity of system components to achieve loose coupling among components. This will minimize the number of components that are in series and thus could cause a system failure. Redundancy, increasing components redundancy, either with parallel operating components or through the use of switches that automatically transfer control and operations to backup components. Multiple functional paths, a technique to increase reliability without necessarily adding redundant components, involves including functional multiple paths within the system design. This is something known as channels of operation. There's also derating components. Derating refers to the technique of using a component under stress conditions considerably below the rating performance value to achieve a reliability margin in the design. So several methods and formal techniques exist to analyze failure modes, effects, and mitigation strategies. Five common techniques are failure mode, effects, and criticality analysis, fault tree analysis, critical useful life analysis, stress strength analysis, and reliability growth analysis. The reader or the listener, I should say, is encouraged to explore any of these techniques as effective analyses strategies, and we're not going to be talking about that anymore. That was a long discussion on reliability. Let's talk about maintainability. Maintainability of a system is a measure of the ease of accomplishing the functions required to maintain the system in a fully operable condition. System maintenance takes two forms. One, repair if the system fails during operation. Two, schedule periodic servicing, including testing to detect and repair failures that occur during standby. High maintainability requires that the system components and their physical configuration be designed with an explicit and detailed knowledge of how these functions will be carried out. Since to repair a system failure is first necessary to identify the location and nature of the fault, that is, to carry out a failure diagnosis, system design should provide for means to make diagnosis easy and quick. In case repair is needed, the design must be dovetailed with logistic support plans to ensure that the components or component parts that may fail will be stocked and be replaceable in minimal time. Unlike hardware faults, replacement of the failed component is not as an option for software because software failure result from faults in the code. Instead, the error in the code must be identified and then the code modified. This must be done with great care and to change configuration documents to prevent the same fault from causing failures in other units of the system. The correction must be incorporated in the programs. Thus, the software maintenance can be a critical function. A measure of system maintainability during operation is the mean time to repair, or MTTR. The term time to repair is a sum of the time to detect, diagnose the fault, time to secure any necessary replacement parts, and the time to effect the replacement or repair. The time to restore also includes a time to restore the system to full operation and confirm its operational readiness. There's also something called built-in test equipment, or BITE. A direct means for reducing the MTTR of a system is to incorporate auxiliary sensors that detect the occurrence of a fault that would render the system inoperable or ineffective when called upon. Then signal an operator that repairs are required and indicate the location of the fault. Such built-in equipment effectively eliminates the time to detect the fault and focuses on diagnosis on a specific function. Examples of such built-in fault detection and signal devices are present in most modern automobiles, which sense and signal any fault indications of airbag or anti-lock brake status, low oil level, or low battery voltage, and so on. In controlling complex systems such as aircraft controls, power plant operations, and hospital intensive care units, such devices are absolutely vital. In automatically reconfigurable systems, the built-in sensors provide signals to automatic controls rather than to system operators. The use of built-in test equipment, or BITE, like I already mentioned, presents two important system level problems. First, it adds to the total complexity of the system and hence to potential failures and costs. Second, it is itself incapable of false indications, which can in turn impact system effectiveness. Only when these problems are examined in detail can a good balance be struck between not enough and too much system self-testing. Systems engineering bears a principal responsibility for achieving such a balance. Then we have thoughts on design for maintainability, the issue that must be addressed to ensure a maintainable system design begin in the system level and range all the way down to include component part includes. And I'll just quickly go through this and you can see the textbook for more detail. Modular system architecture, number 1, 2, replaceable units, 3, test points and functions. So those are stuff that you can explore further. So to achieve the above, there must be an emphasis on design for maintainability throughout the system definition, development, and engineering design process. In addition to the design, comprehensive documentation and training are essential. We also have availability. That's the next major point, and we'll skip over the math related to this as well. An important measure of the operational value of a system that does not operate continuously is referred to as a system availability. That is the probability that it will perform its functions correctly when called upon. And so see the textbook for details about that. Finally, we have producibility for systems that are produced in large quantities, such as commercial aircraft, automotive vehicles, or computer systems. Reducing the costs associated with the manufacturing process is a major design objective. The characteristic that denotes relative system production costs is called producibility. The issue of producibility is almost wholly associated with hardware components, since the cost of replicating software is only that of the medium in which it is stored. Design for producibility is a primary province of the design specialist. However, system engineers need to be sufficiently knowledgeable about manufacturing processes and other production cost issues to recognize characteristics that may inflate cost and guide design accordingly. Such understanding is necessary for the system engineer to achieve an optimal balance between system performance and cost. Some of the measures that are used to enhance producibility are, and I'll just quickly go through these: maximum use of commercially available parts, setting dimensional tolerances of mechanical parts well within normal precision, design of subassemblies for automatic manufacture and test, maximum use of stamping, casting, and other forms of suitable high rate production, use of easily formed or machine materials, maximize standards of subassemblies, and maximize use of digital versus analog circuits. So next, let's talk about risk management, and this will be the final topic here. Many of the methods of risk mitigation listed in another chapter, and we talked about in the detail before, are pertinent to the component design step in the engineering design component. Components contain residual risk factors must be subjected to special technical and management oversight, including analysis and testing to ensure the early discovery and resolution of any design problems. When the acceptability of a given design requires testing under operational conditions, As in the case of user interfaces, rapid prototyping and user feedback may be in order. In exceptional circumstances where the risk inherent in the chosen approach remain unacceptably high, it may be necessary to initiate a backup effort to engineer a more conservative replacement in case the problems with the first line design cannot be resolved when the design must be frozen. Alternatively, it may be wise to seek relaxation of the stringent requirements that would produce only marginal gains in system effectiveness. All the above measures require system engineering leadership. Well, let's get into the fourth major part of what we're talking about in this chapter, and that's with design validation. So design validation proceeds at various levels throughout the engineering development stage of the system lifecycle. So what we're focusing on here is the validation of the physical implementation of the components system building blocks. So we'll have three major things and some points related to those. We'll talk about test planning, developmental testing, and qualification testing. So first of all, test planning. Planning the test of components to validate their design and construction is an essential part of the overall test and evaluation plan. It covers two types of tests: development testing during the component design process and unit qualification testing to ensure that the final production design meets specifications. Component test planning must be done during the early part of the engineering design phase for several reasons. First, the required test equipment is often complex and requires a time to design and build comparable to the required for the system components of themselves. Second, the cost of the test tools usually represents a very significant fraction of the system development cost and must be provided for in the total cost equation. Third, test planning must involve design engineers, test engineers, and system engineers in a team effort, often across organizational and sometimes across contractual lines. From these detailed plans, test procedures are derived for all phases of the test operations. As in system level test planning, system engineering must play a major role in the development of component test plans. That is, what should be tested, at what stage in the development, to what degree of accuracy, what data should be obtained, and so on. An important system engineering contribution is to ensure that component features that were identified as potential risk are subjected to tests to confirm their elimination or mitigation. Next, for component fabrication, part of this general discussion, we've had two sections that looked at the design process, and it was discussed in terms of the objectives and has been related to design decisions defined in terms of drawings, schematics, specifications, and other forms of design representations as expressed on paper and in computer data. To determine the degree in which a design will actually result in the desired component performance and whether or not the component will properly interface with the others, it is necessary to convert its design to a physical entity and test it. This fabrication and this requires the hardware element to be fabricated and individual software components be coded. Prior to fabrication, reviews are held between the designers and fabrication personnel to assure that what has been designed is within the capabilities of the facility that has to be built. The implementation process is seldom unidirectional. Design deficiency are often discovered and corrected during implementation, even before testing, especially in hardware components. Even though CAD has greatly reduced the probability of dimensional and other incompatibilities, it has to be anticipated that some changes will need to be made in the design to achieve a successful functioning product. At this stage of component engineering, the tools that are to be used in production are seldom available for use, so the initial fabrication must be carried out using manual operated machines and hand assembly. It's important, however, that a realistic experimental replica of the fabricated process fabrication process be employed for any component part that are to be built using unconventional manufacturing processes. This is essential to ensure that the transition to production tooling will not invalidate the results of the prototyping process. Involving the production people during sign-off prior to the time of the article reaches the manufacturing facility will greatly expedite production. In the case of complex electronic circuits, significant alterations to the initially fabricated model are to be expected before a completely suitable design is finally achieved. Accordingly, it has been customary to first construct and test these circuits in a more open breadboard or brass board form, so as to facilitate circuit changes before packaging the components in its final form. However, with modern automated tools, it is often more efficient to go directly to a package configuration, even though this may dictate the fabrication of several such packages before a suitable design is finally achieved. Okay, that's all dealing with the test planning. Now let's get into the developmental testing. The objective of engineering development testing is different from production acceptance testing in that the latter is mainly concerned with whether the component should be accepted or rejected, while the former must not only quantify each discrepancy, but also help diagnose its source. Should be anticipated that the design discrepancies will be found and design changes will be needed in order to comply with requirements. Thus, component testing is very much part of the development process. Changes at this point must be introduced via an engineering change notice agreement by all cognizant parties to avoid chaotic, non-coordinated change. Development testing is concerned with validating the basic design of the component, focusing on the performance, especially on features that are critical to the operation within the system or that represent characteristics that are highly stressed. Newly developed or are expected to operate at levels beyond those commonly attained in previous devices of this type. These tests also focus on the features of the design that are subject to severe environmental conditions such as shock, vibration, external radiation, and so on. For components subject to wear, such as those containing moving parts, development testing can also include endurance testing, usually performed under accelerated conditions to simulate years of wear in a matter of months. We also have to be considering reliability and maintainability data. While during development, components may not be built from the identical parts used in the production article, it is good practice to begin collecting reliability statistics as early as possible by recording all failures during the operation and test and identifying their source. This will reduce the likelihood of incipient failures carrying on into the production article. This is particularly important where the number of units to be built is too small to collect adequate statistical samples of production components. Involvement of quality assurance engineers in this process is essential. Development testing must also examine the adequacy and accessibility of test points for providing failure diagnosis during system maintenance. If maintenance of the system will require disassembling the components and replacing subcomponents such as circuit boards, this feature must also be evaluated. And we also need to be thinking about test operation. Component development tests are part of a design process and are usually conducted within the design group by a team headed by the lead design engineer and composed of members of the design team as well as other staff experienced in testing the type of component under development. The team should be intimately familiar with the use of test tools and special test facilities that may be required. The validity and adequacy of the test setup and analysis procedure should be overseen by system engineering. An important lesson that system engineers must learn is that the apparent failure of a component to meet some test objective may not be due to defective design, but rather to a deficiency in the test equipment or test procedure. This is especially true when a component is first tested in a newly designed test setup. The needs for testing the test equipment occurs all too frequently. This is a direct result of the difficulty of ensuring perfect compatibility between two or more interacting and interfacing components, whether they are system elements or test equipment units. Thus, a period of preliminary test should be scheduled to properly integrate a new component with its test equipment, and test unit testing should not begin until all of the test bugs have been eliminated. There also needs to be some mechanism for change control. It will be recalled that the critical designer view that the detailed design of complex system is frozen and placed under formal configuration management. This means that thereafter, any proposed design change requires justification, evaluation, and formal approval, usually from a configuration control board or equivalent. Such approval is usually granted only on the basis of written engineering change requests containing a precise definition of the nature of the deficiency revealed by the test process and through an analysis of the impact of the proposed change on system performance, cost, and schedule. The request should also contain trade-offs of alternative remedies, including possible relaxation of requirements and in-depth assessment of risk and costs associated with making the change. This formal process is not intended to prevent change, but to ensure that they are introduced in an orderly and documented manner. Finally, we have qualification testing. Testing a productionized component prior to its delivery to the integration factory is very much like acceptance testings of units of off the production line. Qualification tests are usually more limited than development tests, but are frequently more quantitative, being concerned with the exact conformance of the unit to interface tolerances so as to fit exactly with mating system components. Accordingly, equipment must used for this purpose should be much like production test equipment. Qualification tests are generally more severe than the conditions to which the article is subject in operational use. The validation of the design of an individual system component can be rigorously accomplished only by inserting it into an environment identical to that which it will operate as part of the total system. In the case of complex components, it is seldom practical to reproduce exactly its environment. Therefore, a test setup that closely approximates this situation has to be used. The problem is made more difficult by the fact that components are almost always developed and built by different engineering groups, often by independent contractors. In the case of software programs, the designers may be from the same company, but generally do not understand each other's design in detail. The system developer thus has the problem of ensuring that the components designers test their products to the identical standards to be used during system integration. The critical point, of course, is that each component interface must be designed to fit exactly with the connecting components and with the environment. So tolerance is another thing that needs to be thought about. The specification of component interfaces to ensure fit and interchangeability involve the assignment of tolerances to each dimension or other interface parameter. Tolerances represent the positive and negative deviation from a normal nominal parameter value to assure a proper fit. The assignment of tolerances requires striking a balance between ease in manufacturing on one hand and assurance of satisfaction, fit, and performance on the other. Whether each producibility or reliability is significantly affected, the system engineer needs to enter the process of setting the preferred balance. There's also computer-aided tools, or CAD. The widespread use of CAD and CAM, computer-aided manufacturing, has greatly simplified the above problem in many types of equipment. With these tools, component specifications can be converted into digital form and directly used in their design. The CAD database can be shared electronically between the system developer and component designer and producer. The same data can be used to automate test equipment. In the area of electronic equipment, the widespread use of standard commercial parts, from chips to boards to cabinets to connectors, has made interfacing much easier than with custom-built components. These developments have produced economies in test and integration, as well as component cost. Miniaturization has resulted in a greater number of functions being performed on a circuit board or encapsulated in a circuit chip, thereby minimizing interconnections and the number of boards. For test operations, component qualification tests are performed to ensure that the final production components design meet all of the requirements as part of the overall system. Hence, they are much more formal than development tests and are conducted by the test organization, sometimes with oversight by the system contractor. Design engineers support the test operation, especially during the test equipment checkout and data analysis. And then we have test tools, a set of test tools for verifying the performance and compatibility of the system components must be designed to provide an appropriate set of inputs and to compare the resulting outputs with those prescribed in the specification. They are in effect constituted a simulator which models a physical and functional environment of the component, both external and internal in the system, and measures all significant interactions and interfaces. Functionally, such as a simulator may be as complex as the component that it is designed to test, and its development usually requires a comparable level of analysis and engineering effort. Moreover, the assessment of a component's adherence to specified parameters, tolerances, values usually require the test equipment precision to be several times better than the allowable variation in component parameters. This requirement sometimes calls the precision greater than that readily available, involving a special effort to develop the necessary capability. Okay, there's more detail in the textbook, but I'll just finish up with the role of systems engineering. From the above discussion, it should be evident that system engineering plays an essential part in the component validation process. System engineers should define the overall test plan, specify what parameters should be tested, and to what accuracy, how to diagnose discrepancy, and how the test results should be analyzed. System engineering must also lead the change initiation and control process. The proper balance between under-testing and over-testing requires knowledge of the system impact of each test, including overall cost. This in turn depends on a firsthand knowledge of the interaction of the component with other parts of the system and its environment. Next, we'll talk about configuration management. The management of a complex new system has been seen to be resolvable into a series of steps or phases in which each of the characteristics of the system is defined in terms of successively more specific system requirements and specifications. The system engineering process that maintains the continuity and integrity of the system design throughout these steps of system development is called configuration management. The configuration management process generally begins incrementally during the concept exploration phase, which first defines the selected top-level system configuration in terms of functional requirements after a process of trade-offs among alternative system concepts. It then progresses throughout the phases of the engineering development stage, culminating in system production specifications. The configuration management process is described more fully in the material that we've covered, because the intensity and importance of configuration management is greatest during the engineering design phase. The terminology of formal configuration management includes two basic elements: configuration items and configuration baselines. Each of these is discussed, and we'll talk about that in the next chart. We'll talk about configuration items first, and then we'll get to this table that we're showing here that shows configuration baselines. A configuration item is a system element that is a basis of describing and formally controlling the design of a system. In early phases of system definition, it may be at the level of a subsystem. In later phases, it usually corresponds to that of a component. Like the components, the configuration item is considered as a basic building block of the system, designed and built by a single organization whose characteristics and interfaces to the other building blocks must be defined and controlled to ensure its proper operation within the system as a whole. It is customary to distinguish between hardware configuration items and computer program configuration items because of the basically different processes used in defining and controlling their designs. Next, we have configuration baselines, and that's where we're showing this table. An important concept in the management of the evolution of system design during the system lifecycle is that of the configuration baseline. The most widely used forms are called functional, allocated, and product baselines. The table that we're showing here shows the phases in which each of these is usually defined, the type of specification that describe it, and the primary characteristics that are specified. The functional baseline describes the system functional specifications as they are derived from the system performance requirements during the concept definition phase and serve as the input to the advanced development phase. The allocated baseline is defined during the engineering design phase as the allocations of functions into system components are validated by analysis and tests. The resulting development specifications define the performance specifications for each configuration item, as well as the technical approaches developed to satisfy the specified objective. The product baseline is established during the engineering design phase in terms of detailed design specifications. It consists of product, process, and material specifications and engineering drawings. We also have to be thinking about interface management. It has been stressed throughout this the textbook that the definition and management of the interfaces and interactions of the system's building blocks with one another and with the system environment is a vital systems engineering function. The function is embodied in the concept of configuration management. Irrespective of whether or not it is formally defined in terms of configuration items and baselines, as described above, it is therefore incumbent on project management with the aid of system engineering to organize the necessary people and procedures to carry out this function. Preliminary condition for effective definition and management of the given interface is to ensure that the involvement of key persons and organizations responsible for the design of the configuration items. This is generally accomplished by means of interface control, interface configuration working groups, or their equivalents whose members have the technical knowledge and authority to represent the organizations in negotiating a complete, compatible, and readily achievable definition of the respective interfaces. In large systems, formal sign-off procedures have been found to be necessary to ensure commitment of the parties to the agreement upon interface control documents. The form of these documents is a function of the type of interface being documented, but during the engineering design phase, it must be sufficiently specific in terms of data and drawings to specify completely the interface conditions to that the individual components developers may design and test their products independently. Then we have change control. Change is vital to the development of a new and advanced system, especially to take advantage of evolving technology to achieve a sufficiently advanced in system capability to provide a long, useful life. Thus, during the formative stage of system development, it is desirable to maintain sufficient design flexibility to accommodate relevant technological opportunities. The price of such flexibility is that each change inevitably affects related system elements and often requires a series of adaptations extending far beyond the initial area of interest. Thus, a great deal of system engineering analysis, test, and evaluation is required to manage the system evolution process. Okay, well, that's a good summary of that material. All right, well, let's do a summary review. We've covered a lot of material, and even so, there were some portions that were skipped in the textbook chapter. So you can refer back to that to get some more details as you would like. So let's take these one at a time. First of all, implementing the system building blocks. The objectives of the engineering design phase are to design system components to performance, cost, and schedule requirements. The phase also establishes consistent internal and external interfaces. Engineering design culminates in materialization of components of a new system focused on the final design of the system building blocks. Activities constituting engineering design are requirements analysis, identifying of all interfaces and interactions, functional analysis and design, focusing on modular configuration, component design, designing and prototyping all components, and design validation, testing and evaluating system components. We also have requirements analysis and external system interfaces. Requirements are especially important at this point in development. User interfaces and environmental interactions require particular attention. Then we have functional analysis and design. Functional design stresses three areas: modular configuration, simplified interactions, software design, modular architecture, user interfaces, effective human interaction, and modular partitioning groups tightly bound functions together into loosely bound modules. We have component design. Major defense and space system engineering is performed by two steps: a preliminary design followed by a critical design review. Engineering design process is focused on configuration items. These are subsequently equivalent to components as defined in the textbook, and we talked about that in this lecture. Preliminary design has the objective to demonstrate that chosen designs conform to system performance and design requirements that can be produced within cost and schedule goals. The preliminary design review centers on major interfaces, risk areas, long lead items, and system level trade studies. Detailed design has the objective to produce a complete description of the end items and looking at the total system. The CDR, critical design review, examines drawings, plans, and so on for soundness and adequacy. Within detailed design, CAD has revolutionized hardware implementation. Mechanical component design can now be analyzed and designed in software. Digital electronics is miniaturized, standardized, and does not need breadboarding. Reliability must be designed at the component level where interfaces, environments, and workmanships are vulnerable areas. Additionally, software must be built to exacting standards and prototyped. When extreme reliability is required, it is typically achieved by redundancy. Measuring reliability usually includes the mean time between failure, MTBF. Maintainability requires rapid fault detection and diagnosis and repair. MTTR is used as a typical measure of maintainability. Mean time to replace. BITE built-in test equipment is used to detect and diagnose faults. Availability measures the probability of the system being ready, and when called in, availability increases with MTBFB and decreases with MTTR. Producibility measures the ease of production of system components and benefits from the use of commercial components, digital circuitry, and broad tolerances. We also talked about design validation. Test planning must be done early since test equipment requires extensive time to design and build. Additionally, test costs must be allocated early to ensure sufficient resources. Finally, test planning is a team effort. Development test is part of the design process and should start accumulating reliability statistics on failures. These test failures are often due to test equipment or procedures and should be planned for since changes are After critical design review are subject to configuration management. Qualification testing validates component releases to integration and focuses on component interfaces. Regardless of the testing phase, tools must be consistent with the system integration process. Finally, we have configuration management. Configuration management is a system engineering process that maintains continuity and integrity of system design. Configuration baselines defined in major system developments include functional baseline, allocation baseline, and production baseline. The configuration items in a system element used to describe and formally control the system design. Okay, that's it for this lecture. Thank you very much.